Okay. Yeah, so hi and welcome everyone to our second exercise course, where we will accordingly talk about the second exercise sheet with the topics Taylor expansion on convexity. So in one exercise we have even both at the same time, which I found quite nice. So, but we will first of all look at Taylor expansions on their own. And yeah, we want to have a warm up, no? Also to somehow memorize, to see the definition of Taylor expansion also on a concrete function. And the function we pick here is this beautiful product function of sine and cosine, where we apply the sine on the first component of our vector and then multiply it with the cosine of the second component of our vector. So two-dimensional function. And we want to do the Taylor approximation of this function around this value of a, which is the zero vector, and we will look at the zero first and second order of the Taylor approximation, and we will see why we have made life a bit easier by picking this value a. So let's start with the zeroth order Taylor approximation. What is the zeroth Taylor approximation? It's the one where we are fitting a constant value to approximate the function at hand. And well, the constant value we pick is simply the value of the function at this approximation point a. All right, so plugging in the value of a, which is the zero vector, into our function we have here, we get here sine of 0 times cosine of 0. But as we will use this a couple of times, cosine evaluated at 0 is 1, and sine evaluated at 0 is 0. So what we see is this thing here is 0. We multiplied something to a 0, it's still a 0. So the constant we use to approximate our function at this point is simply the zero constant. And well, is intuitively also the best way to do. So you want to approximate a function at a specific point, and you don't want to include complicated terms. So the zeroth order Taylor approximation is the most uncomplicated way to approximate it, namely by constant. And the best constant to use is, of course, the function value at this point. And needless to say that this is in many cases not the best approximation, especially when we move away from this point around which we do the approximation. So if you go left, right, or in the two-dimensional also to the diagonal. If we move away from this point, definitely this approximation won't be the best anymore. So what we can do is we can do a more sophisticated approximation and include a linear term. This is what the first order Taylor approximation is doing. It's doing a linear approximation of the function at that point. And well, we saw that in our revision of the Taylor expansion. The linear function we are doing is essentially the Taylor approximation of order 0, and we add to this the inner product of the gradient of the function at that point and multiply this with x minus a. So essentially it is fitting the best line at that point, or hyperplane if we are in a two-dimensional scenario. And well, as we see here, what we will need is definitely the gradient. So the gradient of the function f. So what's the gradient? We have the function here. It's a product of first component plugging into sine, second component plugging it into the cosine. If we look at the partial derivative of this function with respect to the first component, well, then this cosine is nothing else than a constant term. And we only have to, so you remember, this was a bit rushed perhaps in the last exercise, but I try to give you one way to memorize what is the relationship between the derivatives of sine and cosine. Yeah, so here at p half, you have that the cosine is 0, while the sine is 1 at this point. So this is the sine, this is the cosine. So you see, all right. For this interval, I see cosine is decreasing, so it should have a negative value, but the sine is on this interval positive, so accordingly the derivative must be minus sine of x. Similarly, sine is increasing on this interval. So the derivative should be positive, and cosine is positive on exactly this at this range. So you're safe. We don't have to multiply here with a -1 for cosine. All right, and then using this, what do we get if we look at the partial derivative again of our function f? With respect to the first component, sine of x1 is then cosine. So looking at this partial derivative with respect to x1, we get this one here, and the cosine term we are multiplying here is a constant. Similarly, if we switch the roles, now we look at this thing essentially and take the derivative with respect to the second one. We end up with this here, and don't forget the minus. This is coming from this one here. So this is our gradient. We plug it into the first order Taylor approximation. We recall again the formula for the Taylor approximation. So zeroth order Taylor approximation plus inner product of the gradients evaluated at the approximation point times x minus a. Plugging in what the a is the 0 vector. So here at the end, this a is of course not relevant. We know from the previous that this here is the same as the 0th order Taylor approximation, which was 0. So we only care about what this inner product here is doing. We plug in the gradient, which we have computed here. Now, this is what we get here. And well, again, this here is a 0. This here is a 1. This here is a 1. And well, if we compute the inner product with an x, what remains is only the first component of the x. So you see the first order Taylor approximation for this function we have is essentially only looking at the first component of x. All right, then one might wonder, okay, a linear function might not be the best fit for a more complicated function like sine and cosine product of it. So the second order, a quadratic function might be a better way. And this is what the second order Taylor approximation is doing. It is also considering a quadratic term. Now, a quadratic term which is also taking into account the curvature of the function, which is more or less represented by the Hessian matrix, the second derivative of the function. And well, let's compute the Hessian matrix first and then plug it into the Hessian. So what do we have? The gradient, in its first component, this product of the cosines. We take the derivative with respect to the first component. All right, we get then a minus sign of x1 multiplied with the cosine. So this is what we get here. So the second partial derivative with respect to x1. This is, if we look only at the first component of the gradient and then again differentiate with respect to the first component, then we can do the same, but now we first computed the derivative with respect to x1, and then from that one, the one with respect to x2. And well, here what do we get? Well, cosine x2 partial derivative with respect to x2 is minus sine of x2 and then multiplied with the one before. So you have the minus here in front of the matrix. Then, of course, we could, but we are lazy, or let's put it like this, we are clever, clever as we are. We don't have to compute this entry here because the function is continuously differentiable infinite many times, to be exact. So we know the Hessian matrix is symmetric. So the terms are the same due to Schwarz theory. Pardon?
Because that's where my solution differs from yours. Because if I look at the gradient, and so the double sines, but to give the partial derivative with regard to the first component, I get no minus at the end.
Okay, good. Then let's see. All right, we look at the second component of the gradient, and now we have to differentiate here with respect to the first component, right?
Yes.
Okay, but we have a minus in front of that, and then
compute
the derivative, and then it's minus cosine x1 times sine x2.
I thought I took it as even for this partial derivative to replace the second sign as a constant, because it's the second component we want to compute with regard to the first component. So it's like minus sine or minus a sine. A is a constant, that's substituted. And now if I take a minus sign and derive from it, then it becomes a positive constant, doesn't it?
No. So perhaps we can look at it.
We can also draw it. That's how I understand. If the normal sign, the cosine. The line is just another constant.
Exactly. So what we would have here is, so the first, the second component is minus sine x1 cosine, sorry, this is not sine, is it right? Sine x2. Yeah. And now you differentiate it with respect to x1, and what is constant here is exactly this is constant, so or minus sine x2. This is simply a constant. And well, what is the derivative of that thing with respect to x1? It's simply cosine, and then you multiply it with minus the, or multiply it with the constant, which is then that one. Yeah?
Yeah.
Okay. So it would be minus. But this is what I've said. It's also a way to have a sanity check whether you computed something wrong or not. So the Hessian matrix, well, it will be it will be symmetric because all the functions we will look at in our computations, they are all infinitely often continuously differentiable. So the Hessian matrix needs to be symmetric. Yeah. But this is one way to have a sanity check, of course. All right, good. So then this component here, this is, of course, this needs to be computed. It's the one where we look at the second, or the derivative 2 times with respect to the second component. And well, here, same procedure essentially, but we only flip the sine to a cosine for this x2 component. Okay, and now what we are interested in for the second Taylor approximation is the Hessian of the function f at our approximation point we are interested, and it's 0, 0. But as in every component in the matrix, there is a sign, yeah, and sign at 0 is 0. All these entries here are 0. So, well, we can of course write it down, but it's quite clear the additional term which comes into play in the second order Taylor approximation will vanish, yeah, because you're having here the 0 matrix. You have here the 0 matrix in the quadratic form, and well, you can do any quadratic form you want. It will be a 0 at the end. So what remains, in fact, is only the first order Taylor approximation, which is simply the value of x in the first component. So you see, there could be also cases where the first order and the second order Taylor approximation are in fact the same. Yeah, so here are the same. Of course, this is due to the choice of the approximation point. If we would slightly vary the approximation point, we would indeed have here a quadratic term. So if we would go a bit away from the 0 vector, then we don't have here any zeros anymore. Yeah, so here we indeed have and all entries are non-zero, in fact, and the quadratic term would reappear, so to speak. Yeah, but
until we reach a multiple of 2 pi.
pardon?
Until we reach a multiple of 2 pi. Like if A is 2 pi,
yeah,
then we would show vanish again.
Yeah, sure. Due to the periodic behavior, yeah, sure. With the A, due to the periodic behavior of sine and cosine, you have that if you multiply here with 2 pi, you always get the 0 matrix. Yeah, exactly. But as pardon? I couldn't understand.
It might even have a smaller period than 2 pi.
Yeah, sure. So
because we're mixing sign.
Yeah, exactly. So you can have here multiple ways to come up with the 0 matrix, in fact. Yeah. Also pi half. Yeah. So if you have pi half, then every cosine values here will be 0. Yeah. So you can pick any two values where sine and cosine vanish, and then you get the matrix. But the point is, I would like to make is simply you can have the same approximation terms, yeah, depending on the value you are considering for the approximation, but of course, in general, they will not coincide.
Different question. It doesn't matter here because it's method.
Hmm?
Would you need to transpose the second word derivative also? Or is that always an answer? Because we're transposing the gradient.
Yeah.
Before we multiply the exponent.
Yeah, exactly.
We don't need to do that for the second problem. We don't need to do that.
So you are referring to this notion here, or?
That's fine.
In the first Taylor approximation means that you transpose the gradient so that you can keep the scalar product.
Yeah.
Yes, but the Hessian matrix in the second order Taylor approximation is not transposed.
Okay. Okay. This is a good question. So whether it plays a role, whether okay.
Because symmetric, it doesn't matter in this case. Right?
Sure. Yeah, interesting question.
So since in the end we end up with a scalar again, because like no matter how which order you compute multiply the first multiply with the vector transpose, and then with the untranspose vector. So in that you get the same computations.
I'm not sure about that, in fact. So I guess you can easily construct here examples where this is different. But I think the point is for the second order Taylor approximation, you assume that it's 2 times continuous differentiable. This is the thing, yeah, that transposing here doesn't make any difference. But if you would drop this assumption, this is interesting. I haven't thought about that. What happens here? Well, we have to construct first.
Off the recording, right? That might be boring.
Yeah. I mean, we have to first off think of a function which is not continuous anymore when we compute the second. Okay, I mean, it's not so difficult to construct one, but still. Yeah, but we can perhaps.
The third order, we might have to transpose it then.
For the third order? Yeah, for the third order, it's that's a different story. I guess we should leave it as this, but perhaps discuss this offline without the recording. I guess this is a bit more going into the mathematical direction, which you are interested, I see. Okay. All right, good. So this was a short warm-up for computing Taylor expansions. Now, this is what I mentioned with the combination of our topics of convexity and Taylor expansions. Namely, we are now interested in other Taylor expansions or Taylor polynomials, Taylor approximations, however you want to call them. Are they convex? Yeah? Are they even convex in general? So let's start first with the first order one. Yeah, so we could have also looked at the zeroth one, but this is definitely boring because the constant is a convex function. It's although both, yeah, so it's convex and concave at the same time. All right, but let's have a look at the first order Taylor approximation. Yeah, so you are now recalling how it looks like. Yeah, so this is this linear function in x we have, and we have in fact multiple ways how to prove, how to show that this is indeed a convex function, and I will show you all 3. Yeah, I think so. Yeah, and the most straightforward way is, of course, using the definition of convexity as it is. So what is the definition of convexity? Let's recall it. Yeah? I think doesn't do any harm. Yeah? So the definition of convexity, this is what we have here. So we call a function convex if the domain of the function is convex. We used in our lecture always the set S for the domain. Here I write now domain of F. And it's not enough that the domain is, of course, convex. The function has also to do something. Namely, it has to fulfill the following property. So any two arbitrary points we pick from its domain and convexly combine them with some convex combination weight lambda, lambda and 1 minus lambda, in fact. And if we evaluate the convex combination with the function f, then this function value should be smaller than or equal. Then first evaluate the points x and y respectively with f, and then do the convex combination with lambda. So you remember this is if we have here the x, here the y, the condition is telling us this left-hand side, which is everything here, is always smaller than or equal than the line we get if we combine the two function values x and y. The direct definition of convexity. Okay, then what we have to show is that the first Taylor approximation of f is indeed fulfilling this inequality. And as we will see, and of course it's quite clear that this will be the case because it's a linear function. So for linear function, it's quite clear that this is true, but nevertheless, let's do the extra round. So we plug in a convex combination into the Taylor approximation around a fixed point A. What is this? Well, we have to so where is this value appearing? In the Taylor approximation, it's here the x we have here. So we do the substitution here, where we substitute the x with this convex combination with the x and y, right? And now what we can do is we write we write this f of a here, we write it in a more complex way. Namely, we write it also as a convex combination with itself, with the same length. So f of a is definitely the same as if we multiply a lambda to f of a and then add to this 1 minus lambda f of a. Just a more complicated way to write it. And we can do the same. We can do the same for which color I use? Violet. We can do the same for this a here. We can also write it in a more complicated way. Wait, do I have a? No, it's fine. So perhaps I should include the minus, then it's clearer. So we can write the minus a also in the same manner. We do the convex combination of a with itself with some arbitrary weight parameter lambda, and of course this is the same. And now all we need to do is rearrange the terms. So we pick the ones which are depending on lambda. This is that one, this is that one, and that one. And if we arrange them, we see, all right, this is f of a plus inner product of the gradient a with x and minus a, and the lambda is in front of it. And now we collect all the terms which are with the minus lambda. This is that one, and that one, and they are essentially the same as you had before. Only difference that you have here the y instead of the x. Yeah. Okay, but the gray one. So here I haven't included the. So the 1 minus lambda is of course also included. And now the gray one. This is nothing else than lambda times the first Taylor approximation at x, or evaluated x around the point A. The pink one, or whatever color this is the first order Taylor approximation around y for A. No? And okay, then we have shown that this inequality is in fact an equality for the first order Taylor approximation. Yeah, so this is how you can also see that the first Taylor approximation is in fact both. It's convex and concave, because for concave this inequality would be reversed. And if it's equal, if this equality or this inequality holds with equality, then which is the case for linear functions. Taylor approximation, first order Taylor approximation, a linear function. So it's both convex and concave at the same time.
We also need to show that the domain of that is a convex set.
This is, I mean, more or less assumed by definition. So of course we could have here restricted it to some subset, but yeah, you are right. So essentially we need to show that the domain is convex, but it's Rd in fact, which is convex. So take an arbitrary convex combination of two d-dimensional vectors, it's still a d-dimensional vector. Yeah, but you're right. Okay, second variant, and this is of course using the equivalent definitions of convexity, namely the first order characterization, which we also used a couple of times in the lecture today. What is the first order characterization again? Let's briefly recall it. If the function is differentiable, this is important. If it is differentiable, then we have the following equivalence between convexity and what is called the first order convexity, namely the function value of f at some point y is always underestimated by the first order Taylor approximation around some other value x. Now we do the approximation around x. This is again our typical picture we have. We have this function here and we do a Taylor approximation. Oh no, what did I do? Oh, I opened a new session, sorry. I just wanted another color. And what we do is we do a Taylor approximation around some point, and the entire Taylor approximation, this linear function, is completely under the function curve. This is what we get here. And now this is interesting because what we do is essentially we consider the Taylor approximation, the first order Taylor approximation of a first order Taylor approximation. This is why I've found this a bit interesting. All right, so let's see what is the gradient of the Taylor approximation. So what we have to do is we need to compute the gradient with respect to x of t1. Let's see. So this is our function, the first order Taylor approximation. And well, we compute, so I write here to stress this in the index, we compute the partial derivatives with respect to the x components. But well, this is a linear function. By now, I mean, we also did it extensively in the previous exercise sheet. A linear function, also in the multi-dimensional space, is behaving as in the univariate case. So if you look at the derivatives, partial derivatives, you only get, or what remains is only the constant term in front of that. And the constant term in front of that is the gradient of f. So here we see the partial derivative with respect to x1 will only recover the first component of the gradient of f at that point, the second one, the second, and so on. So we recover the gradient, of course. Okay, yeah. So this is our gradient we get here. And now let's plug in this. So we want that one. We substitute the f with the Taylor approximation, the first order Taylor approximation. And this is what we do here. F is substituted by T1 at A. This is the substitution we do here. And well, what do we get? So the first term, T1 x of A, is the first order Taylor approximation here. And this is the definition of that. Second term is all right, so we only have to plug in the gradient, and we do this here. All right, but now if we look at this side here, we see this term here with the x, and let's say this term with this one, they will cancel out. So here you have the inner product of the gradient f of a with x, and here you have the same inner product but with a minus. With the so should have also included the minus to make it very clear. They are canceling out. And so this is 0. And what remains is, well, inner product of the gradient of f at the point A with y, and the same with the minus a, also inner product but minus a, which we can write conveniently in that. But this is by definition the Taylor approximation of the function f at the point y. This is exactly the definition. So what we see is the Taylor approximation around a point y with a is equal to the or put it differently, the Taylor approximation of the function f around the point a, if you plug in the y, this will be the Taylor approximation of that function if we have as an approximation point the x, exactly the x. A bit confusing, but if you look at it, it's quite interesting. And well, we have here equality, and the inequality is then in particular also fulfilled, so that with the first order characterization we can conclude that it is convex. All right, then third variant, perhaps the most common one to verify convexity of a function, is the second order characterization of convexity, for which, as we learned today, second order is always referring to the second derivative, or the Hessian matrix. So what we also have to assume is that the function f is twice differentiable, so that this characterization holds. And it's stating that convexity of f is equivalent to the Hessian matrix of f at any point x is positive semi-definite. Okay, and this is quite quick to check this. The Hessian matrix of the Taylor approximation is the zero matrix. How can we see this? Let's go down, back here. So the gradient of the first order Taylor approximation is the gradient of f at point A, but there's no x anymore involved, right? So the right-hand side is not depending on x, but what we are interested in right now is the Hessian matrix of the first order Taylor approximation with respect to x. Yeah, I stress this here in the nabla symbol to make this clear. But well, looking at the partial derivatives of this component, you will get here everywhere a zero, of course. Because this is a constant, a multivariate constant, a d-dimensional constant with respect to x. And well, the zero matrix is positive semi-definite. It has non-negative eigenvalues, namely they are all zero. So very quick to check it. Check this with the second order characterization. All right, but I just wanted also to show you how convenient sometimes these characterization can be. Well, obviously the second order characterization was the most convenient one, but it also is giving you or showing you how the equivalences are, that you also have them directly ready. All right, then we can ask the same question, of course, for other orders of the Taylor approximation, and we will be in particular interested in the second order Taylor approximation. Is this always convex? But if this is already stated as a question, it seems to be that this is not always the case. Let's see. And for this purpose, we in fact use, so we could of course do all three variants again, but I would prefer to look at the third variant, right? So it was the quickest one in the case for the first order Taylor approximation. So it might be also the case that it's quite convenient to use it here for the second order Taylor approximation as well. This is the second Taylor approximation, here in the display. And well, it is again first order Taylor approximation plus this quadratic term in x. And okay, let's compute the Hessian matrix of this thing. And yeah, to come to the Hessian, let's go first with the gradient. Well, so the gradient of this thing here, if this is a sum of two functions, the first function is t1, so the first order Taylor approximation, of which we know, this is what we have done before, of which we know that this has gradient f of, sorry, this is not correct, this is a copy-paste without the transposing. We know of the first order Taylor approximation gradient that this is the gradient of f of a, so we only need to care about the gradient of this thing here. Let's call this g of x, and we are now interested in the gradient of g of x. And well, this is a quadratic term. Unluckily, I have not the slide ready at hand, but perhaps it's worth to look at it, to get it quickly. Just a second. was here, right? Ah, yeah. I was okay. Yeah. Now we have to do this a bit smaller. So in our revision about multivariate differentiation, we had exactly functions of that kind. Yeah, so there we had also a similar function g, where we only need to do the following substitution, namely b is, sorry, b is f of a half. Not exactly, because we also have here x minus a transpose, but the a transpose terms, or the a terms, they are not so relevant, yeah, because, well, only the x terms are in fact of interest. Yeah, so we could also do kind of substitution. And what we see is the gradient of such a quadratic form, this would be, now it's a bit hidden because it's better. The gradient will be b transposed plus b and then the x. So what we get, yeah, doing the same substitute, so making a substitution, x is equal to x minus a. This is also a substitution we have. We get here that this here is b transposed plus b x, and now we do the substitution back, and if we do this, we end up exactly with this term here. So if we do the, well, we have here that the function f is continuously differentiable. So the Hessian matrix f of a is symmetric. So here we have 2 times the same matrix. We add it up. 2 times same matrix is, and then multiplying with 1/2 is only the matrix itself. No? This is how the Hessian matrix looks like. All right, and this is only the gradient, but we want the Hessian, and well, for the Hessian, we have to compute now the Hessian of this composition of the 2 functions, of the first order Taylor approximation. From the first Taylor approximation, we know that its Hessian matrix, this was what was making our lives so easy in the previous exercise, it's a 0 matrix. And we only need to care about what is the, what's the Hessian matrix of this function, which we coined here g of x. But again, this is a quadratic function, and we did this also in our revision, which I will show you here. And of course, it's very intuitive what the Hessian matrix will be. Let me scale it on the right way. Yeah. So this is still our function g, what we have here, f of x, with the substitution here, b is equal to Hessian matrix of f at a divided by half, and the x is also substituted with x minus a. And what we see, the Hessian matrix of this quadratic form is simply the matrix B plus matrix B transposed. Okay. But this is then telling us, okay, this here is B transposed, whatever, plus B, if you want it this way. And again, taking this into account, we get this one, right? With the substitution. Yeah, because B is 1/2, don't forget the 1/2. B is symmetric because it's the Hessian matrix of F, so we end up with the Hessian matrix of F, which is intuitive, of course. So what we see, long story short, the Hessian matrix of the second order Taylor approximation is the Hessian matrix of the function f. Makes somehow intuitively sense, but now we also have verified this. And with the second order characterization, we know a function is convex if and only if it's 2 times continuous differentiable, and the second order Taylor approximation is 2 times continuous differentiable. It is convex if and only if the Hessian matrix is positive semi-definite. But here we have equality between the two, between the Hessian matrix of F and the Hessian matrix of the second Taylor approximation. So once the Hessian matrix of F is semi-positive definite at the point A, perhaps this is of T only if, not entirely, this is only if this was perhaps too much, but as this here is positive semi-definite. Sorry, this was perhaps confusing you. F does not need to be convex only at that point around which you do the Taylor approximation. There the Hessian matrix has to be positive semi-definite, and then the Taylor approximation, the second order Taylor approximation, will be a convex function. So it will be bowl shaped with the bowl open, not on the upside down. Sorry, this was still a typo here. Okay, but the Hessian matrix at the point A is not always positive semi-definite, but it will be always positive semi-definite if you have a convex function, of course. Then you will always have here, due to the second order characterization, a convex function with Hessian matrix being positive semi-definite, and then the Taylor approximation of second order will always be a convex function. All right, so I think this was all right. Then let's have a look at the third exercise, where we now want to verify convexity of two functions. And the first function we look at is, so here we have to be careful, because now our domain for the function, is S. It's not the d-dimensional real-valued numbers anymore, but it's something different. It's now consisting of all d-dimensional vectors where the components are between 0 and 1, and where when we sum them up, we get a 1. So in fact, they are showing these d-dimensional vectors we are looking at are probability vectors. So And this here is nothing else than the d-1 simplex, if you had heard of this. And what we define on this function S, set S, is the following function f, where we have now a sum over the components, where we do the following. We multiply the ith component with the logarithm of the ith component minus then the ith component again. Yeah? So we can also write it, if we want, in that way, if you like it more compact. All right, and now we want to show that this is convex. And here, this is now important. Before we had a much easier life because our domain was obviously convex, but now we have to check whether this is indeed true. So what we do is we pick two arbitrary points x and y, which are both in S. And if they are both in S, this means that if we sum their components up, this should be a 1, and this here is overdue because here we have the quantity. So summing up their components leads us to a 1, and the components are all inside 0 and 1. And now let's pick an arbitrary lambda between 0 and 1, and let's use the shorthand notation z for their convex combination with this weight lambda or 1 minus lambda. And all we need to show to verify convexity is that the z is always, again, an element of S, because this is what convexity of a set means. You take any two convex combinations of two elements, and the convex combination still stays in the set. All right, so we need to check two properties. First, that the components of the z are all between 0 and 1. This is done quite quickly. Let's have a look at the ith component for any I you like, 1 till d. And what is this? This is lambda times the ith component of x plus 1 minus lambda, the ith component of y. These things here, all of them, are between 0 and 1. The lambda is coming from 0, is coming from the unit interval 0 to 1. The xi, by definition of S, because it's an element of S. The yi is also between 0 and 1, as it is coming, or the y vector is coming from S. So you add here the things up. So it's quite obvious that you can bound it from below with 0. Everything is greater 0, but at the same time, everything is bounded from above by 1. So you definitely have here something between 0 and 1. Okay. Or if you want it in a graphical way, so you picked here. So if you restrict it to one component, what we have here essentially is somewhere an x and somewhere a y, if you want it this way. And what you do is you convexly combine them. So what you look at is the line connecting the two. Now this is what the zi is doing. And now you can, as you see, you can pick here the yellow and the violet point corresponding to the ith component as you want. You will always stay inside the 0, 1 interval. You cannot leave it if you connect the 2 points. Okay, then second property which we need to verify is that the z's are summing up to 1. This is one property, one of the characteristic properties of the set S. And well, let's have a look. What's the sum over the components of z? Well, we have here the zi, which consists of the following components, namely it's the convex combination of the ith component of x and y, with this. Now, the lambda here is not depending on the sum. We can write it in front. We can also decompose the entire sum into two separate sums. And then the 1 minus lambda are the same, does not depend on the index which we use for summation, can also be written in front. Now we take into account that the x is coming from S, so their components are summing up to 1. The same holds true for, oh sorry, there's something wrong. This is y, 1 of course. Yeah, sorry. Yeah, but the same is true for the sum over the components of y. This is summing up to 1. So what we end up with is lambda plus 1 minus lambda. This is a 1. So in summary, the components of z are also summing up to 1. So S is convex. Yeah. We picked an arbitrary z, which is a convex combination of two arbitrary points x and y, convexly combined them and showed that this is still in S. Then here the printer was not working, so it should be a bold x. And what we will do now is we are in fact interested in this function fx. And this function fx, we can write it, now we will take advantage of the nice properties of convexity, we can write it as the sum of the many functions fi. And what are these functions fi? They are mapping the s to, something real valued. And they're looking simply at the ith summit. So if you look at the function fi, it's only looking at the ith component of the input vector x. And it's doing exactly what is in the sum. So we can write f of x in this convenient way. And now, if we can show that all of these fi's are convex, we have here f of x written as a sum of convex functions. And as we know, convexity is preserved by doing summation over convex functions. So f of x is convex itself. So we have boiled down this problem of showing convexity of the f of x to showing the convexity of these fy's. And this is a bit easier. So of course we could have also done this for the f, but I prefer this way. Because now, if we look at the gradients of f of x, if we look at the partial derivative of this function with respect to a component of x, which is not the ith component, it's 0. So because fi of x is only depending in every term on the ith component of x. If you don't have a component, so please don't forget that this here is x1, so on till xd. And you can take the partial derivative with respect to any of these, but only the partial derivative with respect to the ith component will be something which is non-zero, and the one which is something is the ith component. So this here is 1, I minus 1, I plus 1, d. And why is it logarithm of xi? Perhaps this is what we should clarify. The partial derivative of this thing here, now we can apply here one of our differentiation rules. So here we have to apply the product rule, or we can apply the product rule. Perhaps this is the simplest way, and or both, also some rule. And what we get here is the partial or the derivative with respect to xi. This is 1, and we multiplied xi. There we have then to add xi with the derivative of logarithm. What's the derivative of logarithm? This is that one. And then, yeah, this minus, don't forget the minus, here you get a 1. But this here is obviously also a 1, right? So what we are left with is only logarithm of xi, and this is what we get here. Huh?
Just wondering, extrapolating from xi, you get entries on the diagonal in the Hessian matrix.
Oh yeah, sorry.
Yes.
Yeah. Sorry. There's also, yeah, definitely. No, wait.
You should get it.
No. So no. So what we have here is this entry is the derivative of fi, second one, where we have first computed the x1, or taking the derivative with respect to 1, which is 0, and then we have,
It's 0.
because here you have a 0. So
non-zero for xi, and that I at that position is 1. Is it not?
no. So again, you can also look at it. Yeah. So let's say I is 1.
Okay.
Yeah. Then
So,
you have here logarithm of x1. Yeah. Then of course doing the derivative with the first one is giving you the 1 over x1.
yeah, and that means in that upper column and in the upper left should be x divided 1 divided by x.
Yeah, but you have to read it like this. Yeah, so this is. Oh, my pen is. So you have to read it like this. So this is 1. This is component
Yes.
d, and here the same 1. I minus 1 I.
This is not the complete Hessian matrix. It's just proof regarding.
No, this is This is the complete Hessian matrix
Of fi. And
of fa.
you get the diagonal to that.
Yeah. Okay. Okay. So.
That's why I saw.
Yeah. Okay. Perhaps just to.
Yeah.
So.
Okay, you stay consistent with your.
Yeah.
Approach. Okay. Yeah.
So, just to as a sanity check, perhaps you haven't done this in this way. So, this would be the gradient of the fi's I'm using here, and we recall that this is, we can plug out, write out the sum as this. So the gradient of f would be logarithm x1 logarithm xd, and the Hessian matrix, yeah, you can do the same. It will be the sum of the Hessian matrix of all these fi's, and this would give you, I think this is the diagonal matrix with 1 over x1 and so on the diagonals.
Yes.
Okay.
That's what I expected, and I was like, okay, why?
Yeah. Okay.
Okay. If you just consider the the second partial derivative of the I component, then yes, you only have one entry in the matrix.
Exactly. Yeah, so good then. All right, and then well, we have now both ways. So Fi, the Hessian matrix of Fi is definitely positive semi-definite because all eigenvalues are 0 except one, namely the one where we have, or perhaps not 0. This could also be, no, it cannot be, because so it can be.
It's just one.
Yeah, so the highest one. So xi can be something between 0 and 1. So this is definitely something non-negative. That's all. Eigenvalues are xi and 0, and this is d minus 1 times the eigenvalue. Yeah, in the algebraic.
Just to be sure, the original question was to compute the Hessian matrix of Fi or?
No, the original, so the task was to show that F is convex.
F is convex,
yeah.
not Fi. Although, yes.
Yeah, but before I explained why it's sufficient to explain, derive that Fi is convex, because then as a sum of convex functions, F will be convex as well. This was. I mean, you can do, of course, you can do the analysis right away for the F, but I wanted here to show you somehow that don't forget about the nice properties. So perhaps if you combine or you write your function as sum or whatever supremum of convex functions, then it's fine to show the convexity of the components, which is sometimes easier. Perhaps not in this case. So in this case, I agree that both variants are not exactly, for instance. Okay, so let's keep an eye on the clock and go for the next part, where we have now the following more abstract scenario, which is a bit hidden due to the d times 1, so perhaps not so interesting, because eigenvalues can also be written like this. So we have the following scenario. Now the S is some convex set, so we don't have to care about convexity of the set, because by assumption it is convex. And this will be relevant for our case. We assume that the 0 vector, the d-dimensional 0 vector, is inside the convex set, which is not always the case, of course. So you can also have a convex set where the 0 is not included. But here we will need that the 0 is included. And we look at a very generic function f, which is having the following two properties. First, it's positive homogeneous, is it called? Namely, this means that if you apply or if you multiply some vector x with the value lambda, then it's the same as if you would first apply the absolute value on the lambda and then multiply with the function value of f. The function value of x at f. The second one is more or less subadditivity. Namely, if you look at the function value of x added to x tilde, for any arbitrary x and x tilde in your set S, this is always bounded by first evaluating the two x and x tilde and then looking at the sum of the function values. And by the way, this property is fulfilled by any semi-norm on S. So this is this positive homogeneous property and kind of triangle inequality, something similar in this regard. And for so in particular, any norm, yeah, so every real norm on S or on the d-dimensional real-valued numbers fulfills this property. And it will show you, so what we will essentially show is the Euclidean norm, yeah, the L1 norm, and all the other norms you can think of. All of them are convex functions, if you look at them in that way, yeah, that they are mapping some d-dimensional vector to a real-valued number. Okay, and why do we need to show, why do we need this property that the zero is inside? Because we will later on use that if you have an x and if you multiply a lambda, then lambda times x is still in S. And this is not always the case, but it is the case if S is convex, because you can write lambda of x also as the convex combination of x with the zero, because this is, this here would be zero. Oh, what happened here? This here would be zero. Okay. Why is it jumping? Okay, this is, there's something wrong with the pen. Okay, I will try it by mouse, but I guess this is not working that well. This is the problem. Yeah, so the pen is already almost dead, or it is. Okay, so we have to, I have to point it. Okay, so with a big bit shift, yeah. No, this is not good. Okay, good. I have to explain it then with the cursor. Sorry, the pen is there. So this here, yeah, this is a zero, and well, this is a convex combination, yeah, of something which is inside S with something which is again inside S, namely the zero. So by convexity, the convex combination will still be in S, meaning that lambda of x is still in X. And we can do the same argument for 1 minus lambda of y, for some arbitrary y and an arbitrary lambda. And with this, yeah, it's very obvious why convexity holds. Yeah, we can simply use the definition for convexity. We pick two arbitrary points from our domain. We pick an arbitrary convex weight. We look at the function evaluated at the convex combination of the 2 points with this convex weight. With property, the subadditivity, yeah, I cannot resist. I have to use colors. And I would give it a try.
Yes.
Now.
And doesn't matter for the proof, but the strict shouldn't be the second class equation or line equation. You pull 1 minus lambda out of f of y. But if you apply the second equation strictly, the coefficients should still remain within f of y.
Oh, yeah, yes. So yeah, you're right. Here it's f. This is, yeah. Yeah. Sorry, this is of course a typo.
In the end, it doesn't matter. But
Yeah, sure. In the end, it doesn't matter, but to be, yeah, strictly speaking, you have the f here. Sorry. And then now you can use the second one, or the first one rather, Now you can apply it for this one, and you can apply it for this one. And then what you have shown eventually is exactly the definition of convexity. Yeah, evaluating the function at some convex combination of two convexly combined points is always bounded from above if you first evaluate the points with f and then do the same convex combination. Again, and this is quite nice, quite generic, because it's essentially showing that all the norms on the d-dimensional real-valued numbers are convex functions. Okay, so 10 minutes for the practice exercise, which is, I guess, fine. I mean, it's an add-on of what we have done the last time. So I'm still no Zoom audience. Okay, this should go away. All right, yeah, so it's an add-on of what we have done before. So where we looked at this PyTorch package, which gives us a way to compute gradients. And now we are interested in this case about the Hessian matrix, whether we can also compute Hessian matrix. And yes, we can, of course. So this is also possible. And what we will look at is at the function f first, which we considered last time. And for this purpose, you have to import here the Hessian package, or the Jacobian package is also possible for computing the gradient. So this is another way I wanted to show you to compute the gradient. And what we do in PyTorch is always using these tensor data structure. So we something like a counterpart for the NumPy ND array or the pandas data frame. It's a torch tensor. And well, we also looked at it, what happens if we create such a tensor. Yeah, we can do some print operations on that, and what we get is something similar to what we would get if we would look here at an NumPy ND array. And now, this is what I haven't done last time. What we can do is we can also specify functions, as usual, and use here the function we would like to have. And the function we would like to have is here this exponential function, and then adding up the squared components of the input. This is what you see here. And then we can evaluate it at the value we are interested in, which we have specified here above. And we can also compute the gradient with the Jacobian, because here we have a function which is mapping two-dimensional vectors to the real-valued number, and then the Jacobian is the gradient, essentially. We can also compute then the Hessian, which is the second derivative, using this Hessian operation here, and we can have a look then at that. So the first print is telling us what the function value of f is at the, also here's an x missing, at x1 being 0.5 and x2 being minus 0.25. Here we have the gradient. This is exactly the same gradient we had on the in the previous Python notebook. And here we have now the Hessian matrix. So you see also this two-dimensional array structure. And we can verify this. We are skeptical people. We can verify this because we have computed the Hessian matrix on the previous exercise sheet explicitly. We can plug in the values, and if we do this, we end up here with the same exact values we see here. Okay, then what we want to do is we want to compute the eigenvalues of the Hessian matrix, and for this purpose you can use the linear or linalg, so for linear algebra, subpackage of torch where you have the function eigenvals for eigenvalues. You plug in a matrix, a quadratic matrix, of course, and what you get is again a tensor. Torch is always revolving around tensors. You get a tensor where as an array or torch tensor, you get the eigenvalues. Yeah? And what we see here, it's quite sophisticated because it can also compute the complex. So if you have here a quadratic function which only has complex eigenvalues, yeah, might be the case, but not for symmetric ones. For symmetric, we have no problem. Yeah, there the complex part is, or the imaginary part is always 0. And we can check then quite easily as follows, at least if we use NumPy array, a transformation into a NumPy array. Yeah, so this L can be transformed, the tensor can be transformed into a NumPy array. This is what I do here. And then with a NumPy array, you can do component-wise comparisons, which I do here. Yeah, so this here would check component-wise whether the entries are non-negative. This is what this here is doing. And then you will get a list or a NumPy array where you have true, false, depending on whether this is true. Of course, this is true 2 times for this L here. And then if I look at the product of these things, this is only 1 if this was true all the time. If I have once a 0 here or a false, I will have a 0, so I can check quite easily if here we get a 0, then there must be a negative value between the eigenvalues. And this can be used to check, so to be cautious, we can check numerically. I mean, theoretically you cannot check it, but you can get an intuition whether convexity holds or not, because convexity is really only from a mathematical perspective. You have to check one of the conditions, which we have done on the exercise sheet. But let's keep it like this. So this is one way how you can do this numerically to get a feeling whether a function is convex or not, at least on a specific domain. And the domain we are looking at here is the unit hypercube, 2-dimensional one. And what we will simply do is we compute the Hessian on a grid of the set S. We go here with the first component over with step size 0.05 over the 0,1 unit interval, and then in a second loop we do the same for the x2, and then for each combination of the two we compute the Hessian matrix of our function f at that point, compute of this Hessian matrix the eigenvalues, and then do our check. Is there one negative value in the eigenvalues of the Hessian matrix or not? If yes, then our check will be false, which is true at the end, and we break them. And well, we had this in the last exercise sheet. This function here is convex. So this is a convex function. We could do here, we could make the grid finer and finer, but the check will still be true. This is different for this function here, for the sigmoid function. And it is not depending on the A, in fact, which we are using here. So again, we can do the same consideration, how to get the hash in and so on. But so interesting, let's rather look at what happens if we check now numerically with what happens with convexity. Now we have a three-dimensional function. It's mapping three-dimensional, so we have here 3 for loops nested each other. And then of course here, so this was something I was confused for a while. If you would run this, you get here a problem with float. Therefore, here as type float, then it's working. And what you get here, and I also have here a quite complicated else break continuous structure, because if I leave this out, you will get here that's not all loops are so it's only closing the most inner loop, of course, and then you get here a couple of points where the convexity or the positive semi-definiteness is not fulfilled, but in fact, if you break the entire nested loop at the first point, which you can do in this way, of course, there are also more clever variants, I guess, but this was quick and dirty. And well, what you see at the very first iteration, so you see I used here as the starting point 0, 0, -1. And at this point already you have that one eigenvalue will be negative. So here you see -5, so small but still negative, and so convexity is not fulfilled. So this procedure is better suited to detect non-convexity. So it's you can of course use this to detect non-convexity, but to verify convexity, this is I get a stomach ache. But well, so this is sometimes done in practice, but it's not very clean. Let's put it like this. So even if all the eigenvalues are non-negative for your grid points, it does not mean that your function is convex. It only indicates that it's kind of convex at these points. But definitely you can detect non-convexity in this way. So once you find a grid point where the Hessian matrix is not positive semi-definite, then you're done. Then you have verified that this is not convex. All right, so regarding the time, I don't want to go over the time. I guess from the Zoom audience, there will be no questions. Perhaps from your side, everything. All right. Then, thanks for participating. Thanks for watching, hopefully, and see you next time. Bye.